Take an example of the mass of an object. So let's say you have a car, and in that car, the weight of the car is 1,000 kilos. And in that car, there is a person, there is you standing inside or sitting in that car, and you weigh 60 kgs. And then what you say is that the sum of this entire moving car would be 1,000 plus 60 kilograms. Well, that makes sense. So it's 1,060 kilograms. Now assume some different scenario. In this scenario we talked about the mass of an object. Let's assume that you are in a train, and this is the coach of the train, and within that train, as the train moves forward, so this is very roughly a representation of the train, as the train moves forwards, let's say with velocity 5, you as a person run inside the coach with speed 7, and that would not make sense, right? So let's take the speed to be 1. So 1 meters per second and 5 meters per second. Now I want to know that if someone is sitting inside the train, so if your parent is sitting there, they would see you running with a speed of 1 meters per second within that coach of a train. However, if you take me, who is observing you outside of the train on the ground, and the train is moving, how will I observe you? With what speed are you moving with respect to me, with respect to ground, with respect to Earth in general? In that case, there are many possibilities. So let's fix the velocity of train first. Let's fix the speed of the train first. So let's say that the train moves right, and that just eases the argument a bit. But then you also need to say in what direction that you are running. Then only I can observe exactly what velocity you will have with respect to the ground. So if you run to the right in the coach, to the direction in which the train is moving, so if you move right, in that case, the velocity that I'll observe you with will be 5 plus 1. It will be 5 plus 1. And why? Since the train is already moving at a speed of 5, and inside that train you're moving with an additional speed of 1 meters per second. So in that case, I would observe you moving with a speed of 6 meters per second. But if you move left, that is, you move opposite to the direction of motion, in that case, I would not observe you with 6 meters per second. Then the train would still move at a velocity of 5, at a speed of 5 or velocity of 5, whatever you say. But now, with respect to train, you're now moving on the left side. So you are moving in this side, you're moving in the left side. So let me do that in a different color. So you're moving on the left side, and so now I will observe you with a speed of 5 minus 1 meters per second, since the train is moving at 5 meters per second, and you, as a runner, are moving opposite to the direction of motion of the train, and so now I will observe you with a velocity of 4 meters per second to the right again. So physical quantities like quantities like velocities need a direction. Now if I would have said speed doesn't need direction. A car moving right with some speed can just reverse its direction, and it will just move back with the same speed. It can do that. However, velocity is something where you need to specify the direction, and that's not just about velocity. Let's take a monkey who is and in fact that there are really good applications of monkeys in physics. And let's take a monkey who is just hanging by a pulley. So let me draw a different monkey. So here is a monkey, and he's hanging by a pulley, and the pulley is fixed at some point, and there is a mass here. So there is mass, let's say m. And now if that monkey, if that animal kind of applies a force in towards him in this direction, in this yellow direction, then he can lift the mass. However, if let's suppose the mass is too heavy for him and this is a free pulley, then the mass will instead pull him and that monkey would reach to the top of the pulley. And so really, things like these, where you need to specify the direction, and this is a really oversimplified example. However, things in which not only the length, the magnitude of a physical quantity suffices your description of that quantity, you also need a direction. Those quantities are known as vectors. Vectors. And so vectors you can say as physical quantities that describe magnitude and direction. Physical quantities that describe both magnitude, and by magnitude I'm meaning things like 5 meters per second or 3 newtons of force or 5 pascals of pressure. Magnitude is just the measurement in general, and not only magnitude, vectors also describe the direction of that quantity, of that physical quantity. So now that you know what vectors are, you can easily specify some vectors, but let's not only think about left and right, up and down as being vectors. Let's take some different examples. So let's take a river, and the river is flowing. These are the banks of the river, and the river is flowing with some speed. Let's take 5 kilometers per hour. So the stream in the river is flowing with 5 kilometers per hour, and you as a swimmer want to cross this river. So you start here, you start swimming here, and you want to reach to the other side of the river. And so you start with some velocity, directed along the path that you want to go. So let's say you start with 10 kilometers per hour and you start swimming with that velocity. Now this is something of common sense, that you won't go in a straight path. You will divert from that. You will go something like a slant path. So, why? Because as you will swim, the river will push you along its flow. So you will experience a velocity that will be a bit tilted towards the other side rather than being completely straight. And in things like this, you again need the definition of a vector. You again need the direction, specifically that you need to specify how the river exactly moves, and then in what direction will be your resultant velocity. The resultant is a concept that we'll get to in next videos, but in what exact direction would you land up? Let's say you land up here, and then what distance you now have to run back to get to the position that you intended to. All of these interesting questions get answered using vectors as a tool to solve problems not only in physics, not only in mathematics, but in science in general. And vectors and scalars are part of what we take as a bigger mathematical entity known as tensors, but we'll get to it in future videos. But for now, we now know what a vector is. A vector is any physical quantity that requires magnitude and direction to describe it. And then the other thing that only requires magnitude are called scalars. Scalars require only magnitude. They don't require direction. So let's take an example of a scalar. So a perfect example of a scalar will be distance. Now, if you want to fly from, let's say you wanted to fly from Chicago to New York, there are multiple ways you could have done that. Now, let's say that the distance between these two places, the distance on Earth, when you measure it with a measuring tape. Let's say the distance is 1,000 miles. And then there are many ways you can do those 1,000 miles. Either you could have just taken an airplane and you would have just flown across those 1,000 miles, and that would have been a pretty efficient way. But now then you could also have done something that would be pretty different, I should say. That you would go from Chicago and you would get to Alaska. You would get to Alaska, and from Alaska you would then take a connecting flight and you would get to New York. And in that case, let's say your Chicago to Alaska flight covers a distance of 500 miles, and I'm really cooking up the numbers, and Alaska to New York takes, let's say it takes 700 miles. Then the distance now you have run, when you now you have traveled in case of a connecting flight through Alaska is 1,200 miles. And you could have really extended this. Let's say after going to Alaska, you want to go to Hawaii, and after Hawaii you go to let's take any other random city in the world. Let's say you went to London, and then from London you went to New Delhi. From New Delhi you went to Beijing, and so on and so forth. And the point here is that given any sort of path that you have run, so something like this, something really different from what would have been the best path, you always run a certain amount of distance, you always travel a certain amount of distance, and that distance doesn't take into account the direction that you have run. So the direction you have traveled, I'm confusing it with run all the time, but the distance really doesn't require any sort of direction. And you could have 1,200 kilometers in one direction is equivalent to saying you have run 1,200 kilometers in somewhere else, and 1,200 kilometers here from A to B, and let's say the distance is 1,200 kilometers, and from A to C the distance is again 1,200 kilometers, then these two have no difference in them. They are one and the same thing. But if you would have thought of something like the exact position difference that you have, that might have been a bit different. And so really just regard vectors as a physical quantity that requires direction to describe it properly, and we'll continue building on vectors as we explore physics, as we explore mathematics, as we explore sciences in general, and let's continue talking about them in the next videos.